In this video, we will discuss the capture zone of a well in uniform flow. This type of work is useful for designing wells to capture contaminant plumes. For example, today, in addition to working through some of the math, I want to pay special attention to the shape of the flow pattern, as this will help us to think through future problems. By uniform, we mean that the background flow is constant with time, not transient, and flows in a single direction. Now, if this flow were to become contaminated somehow, we would like to know how to design and place a pumping well that would capture the contamination so that it could be diverted out of the groundwater system. In this case, the solution of the general groundwater flow equations is given by equation 7.23 in the text. Here, R is the distance from the pumping well in either direction, and A is the hydraulic gradient of the background flow, which can be determined by measuring the hydraulic head and wells placed both upstream and downstream of the pumping well. So in this case, A would equal H1 minus H2 over, I'm just going to call this distance L for now. So that's the background flow. It's not impacted by the pumping that's happening at this well here. The black dashed lines here are again equipotentials, and the blue are streamflow lines. Note that, as always, streamflow is perpendicular to the equipotentials everywhere on this plot. There are just a few. All of the flow paths shown in this image will eventually be pumped out by the well, and so they define the capture zone of the well. There are, of course, also flow, you could draw in flow lines outside of this area. Hopefully they will represent uncontaminated water, as none of that water is going to be pumped out by our well, and instead those flow lines represent flow that is contributing to the background flow. It won't be pumped out. Now, to mathematically define the extent of this zone that pumping is going to impact, we need to examine the solution at point S, which is the stagnation point, where flow stagnates. At this point, there is no flow in either the x direction or the y direction. So we can write that down: no flow in the x direction or in the y direction. The stagnation point is the only point on the x-axis where there is no flow. So we can determine its location by setting the partial derivative of the hydraulic head equation with respect to x equal to 0. And we can find the equation for that is equation 7.26 in the text if you don't know how to take the partial derivative yourself. Okay, so we get this, the change in head with respect to x. We've set that equal to 0, and now what we're going to do is solve for r in order to get the distance from the well to the stagnation point. To do this, we are going to assume the center of our coordinate system is that well. In doing so, we can find the distance from the well to the stagnation point, just like we were trying to do, and this is what we get for that. We can see that the location of this point depends on the discharge, right? The amount of water that's actually being pumped out by the well, as well as the transmissivity of the ground and that background hydraulic gradient, which hopefully all of that makes some physical sense to you at this point. The extent of the flow lines in the y dimension here, as measured from the x-axis, can be found with this formula here, And this little symbol is measured in radians and represents the angle to a line going through the 0, 0 of our coordinate system and extending out to whatever point on the outside of the capture zone that you are looking at. And this equation will then solve for y, which is this amount here. And if you take this far upstream of the well, you approach a solution with this value as the extent of the capture zone in the y dimension. So that's written here if you were to consider just half of that area. And you can see there's only really one thing you can change in this equation, right? You're not going to change the transmissivity of your ground, and you're not going to change the background hydraulic gradient, but you can design wells with different amounts of discharge. And by doing so, you can sort of define how large of a capture zone you might need to capture any contamination that might exist. So here we have the corresponding computer model for the situation that we've already described. Notice all the little arrows here. Those are on the plot in 1 year increments. So it would take 1 year for the flow to travel from this arrow along that flow line to the next, and then 1 additional year to travel to the next arrow, and so on. And if we look closely at the stagnation point, which was right around here, we can see that flow near that area proceeds incredibly slowly, right? It's taking many, many years to traverse not very much ground at all in its flow towards that well. Zooming out again, we can observe the equipotentials and flow lines that develop when you construct a single pumping well in a uniform flow field. And with that, we can conclude the single well in uniform flow video. See you next time.